This video contains the complete solutions to sample exam number 2 for MAT213 Calculus 3. We start off with some multiple choice questions, and the first one is, which of the following vectors is orthogonal to the plane 2x minus 3y plus 4z equals 7? Now what we have to do for this problem is remember that the general form for a plane is ax plus by plus cz equals d, where the vector a, b, c is the normal vector. And that's the vector that's perpendicular to the plane. So a vector that's going to be orthogonal to that plane is going to be some multiple of the vector 2, negative 3, 4. So it could be that vector exactly, or it could be any scalar multiple of that vector. And immediately we should be able to see that option B is that vector, and so that's one of the many normal vectors that we could use. For this next problem, it's the same plane, but now we want to know which of the following vectors lies in that plane. Now remember that the normal vector is normal to any vector that lies in that plane. So what we're going to do is we're going to dot all of these vectors with the vector 2, minus 3, 4. And the one that gives us a 0, that's going to be the one that's orthogonal to the normal vector, and then therefore lies in the plane. So our first dot product works out to be 1 times 2 plus 1 times negative 3 plus 2 times 4, and that's not 0, that's 7. So it's not A. When we dot this vector with itself, we get 4 plus 9 plus 16. That's 29. That doesn't work. For this third vector, we get 2 times negative 2, 0 times 3, 1 times 4. That works out to be 0, so that's the one we're looking for. But just to make sure, just to be thorough, 2 times negative 3 is negative 6, 4 times negative 3 is negative 12, and then 7 times 4 is 28, and that works out to be 10, which is not 0. So the answer is C. Here we have that z is a function of x and y are functions of t, and we want to know how to use the chain rule to compute dz dt. So what we can do here is draw our tree diagram. Z is a function of x and y are functions of t, and that means that dz dt is going to be del z del x times dx dt plus del z del y times dy dt. So the expression we're looking for looks like dz dt is del z del x times dx dt plus del z del y times dy dt. Here we have a bunch of different statements about the gradient, and only one of them is true. And so what we should remember about the gradient is that it points in the direction of steepest ascent, of steepest increase, and that's option A. For the next one, Clairaut's theorem is the theorem that tells us that when we take a partial derivative with respect to multiple variables, the order in which we do the partial derivatives doesn't matter. So in other words, f sub xy equals f sub yx. This time we're looking for the slope of the tangent line to the curve sine of xy equals 0 at the point 2, pi. So what we remember is that when we have a function, when we have a curve that's described by implicitly by a function capital F of x, y equals 0, the slope of the tangent line, dy dx, is negative capital F sub x divided by f sub y. So it's minus the partial derivative with respect to x divided by the partial derivative with respect to y. So the partial derivative of sine of xy with respect to x is cosine xy times the derivative of xy, which is y, divided by the derivative with respect to y, which is cosine of xy, times the derivative with respect to y of xy, which is x. So we can cancel out the cosines of xy, we get minus y over x, so in this case that's going to be minus pi over 2. Here we're asked to compute a limit as xy goes to 2, 2. The first thing that we should try if we see a limit, the very first thing that you should try is to try to plug in those two numbers and see if you actually get a value that you can use. Because if so, then the function is continuous and we're done. But unfortunately, when we try to plug in 2, 2, we end up with 0 divided by 0. And so that means we're going to have to keep working. But it's a good sign when we get 0 over 0 that sometimes means that we might be able to factor the top and factor the bottom and see if we can simplify. And that's how it's going to work for us here. So y squared minus 4 divided by xy minus 2x. Y squared minus 4 factors as y minus 2 times y plus 2. On the bottom we can factor out an x. So now I can cancel the y minus 2's, which gets me y plus 2 divided by x. And now when I plug in the point 2, 2, what I get is 2 plus 2 divided by 2, which is 2. So the next few problems deal with the same function, f of xy equals x squared minus 3xy minus 2y squared. And in this one, we have a diagram where we're given a picture of this function of just one level curve and then 4 potential vectors. And we want to know which one of those vectors points in the direction of steepest increase for f at this point. And remember that the gradient tells us that. The gradient of f at this point 1 comma negative 1 points in the direction of steepest increase. So let's figure out what that gradient is and then use that to figure out which vector we're talking about. So to figure out the gradient, we need to know the x and y partial derivatives. Partial derivative with respect to x is 2x minus 3y, and the partial derivative with respect to y is minus 3x plus minus 4y. When we plug in 1 comma negative 1, what we get is 2 times 1 minus 3 times negative 1 for the x partial, and then negative 3 times 1 minus 4 times negative 1 for the y partial, and that's going to be 5 comma 1. So which one of these vectors points in the same direction as 5 comma 1? Well, that's going to be a vector that points largely in the x direction and a little bit in the positive y direction, and we can see that that's option B. So that vector B is parallel to the vector 5 comma 1. Now for the same function, we're asked to compute a directional derivative. So the directional derivative, d sub u of f 1 comma negative 1, is the gradient of f at the point 1 comma negative 1, dotted with the unit vector that points in that direction. Now we already know the gradient vector is 5 comma 1. Well, what's the unit vector? We have to be careful here. It's not the vector negative 3 comma 4, because negative 3 comma 4 is not a unit vector. We have to figure out the magnitude of that vector, minus 3 comma 4. And what we're going to find is that it's not 1. Negative 3 squared plus 4 squared, that works out to be 5. And so the unit vector is the vector negative 3 comma 4 divided by 5, in other words, negative 3/5 comma 4/5. That is a unit vector. And so that's the vector that I want to dot with my gradient. So I get 5 times negative 3/5 plus 1 times 4/5. That's negative 15/5 plus 4/5, which is negative 11 over 5. And that's my directional derivative. Now for this last question, again, we're looking at the exact same function as before. We want to know which of the following is a critical point for f of x comma y. So we have to remember the x and y partials that we got in the earlier problem. I've got those here. And now what we could do is set both of these equal to 0 and solve that system of equations. But it's actually easier to just take each of these points and plug them in to each of these partial derivatives. So for a, f sub x at the point 0, 0 is going to be 0, and f sub y at the point 0, 0 is also going to be 0. So a is a critical point. Let's just make sure that we don't get any other critical points for our other choices. So f sub x at the point 2 comma negative 3, it's going to be 2 times 2 minus 3 times minus 3. That's going to be 13. And really at that point we can stop, because to be a critical point, both partial derivatives have to equal 0, and here already we see that the x partial derivative isn't equal to 0, so we don't even have to try the y partial derivative. For the next potential critical point, minus 3 comma minus 4, we would plug in 2 times minus 3 times minus 4, and there we get 6, and again that's not 0, so this can't be a critical point because it doesn't even make the x partial derivative equal to 0. And similarly, if we try the fourth choice, 1 comma minus 1, 2 times 1 minus 3 times minus 1 is 5, and again that's not 0, so if the x partial derivative isn't 0, then certainly they can't both be 0, and so that's not a critical point. So just checking how you would check the other options, but the only answer here is a, 0 comma 0. Okay, here we have some practice problems with partial derivatives. So if we've got this function of x, y, and z, then f sub x is going to be the derivative of xy, which is y, plus the derivative of yz squared, since there's no x's in that, that's just 0. And the derivative of 3x is 3, so we get y minus 3. Here again, I'm asking for a partial derivative. I'm using the del notation, so del f del z, that's the partial derivative with respect to z. The derivative of xy is 0. The derivative of yz squared, well, the y is a constant multiple, and the derivative of z squared is 2z. And then 3x doesn't have any z's in it, so that's just 0. So the answer we get is 2yz. And then finally we want f sub yz, so we want the partial derivative with respect to y and z. So we already figured out the partial with respect to z, so we'll just take the y partial of that. So the partial with respect to z was 2yz, so we're taking the y partial of 2yz, which is just 2z. All right, now we have an equation where we want to find the equation of the tangent plane, and so here's what we do. We've got two formulas to find the equation for the tangent plane. One is when we have a surface that's z equals f of xy, but this one doesn't look like it can easily be solved for z because of that z squared. So what we're going to do is subtract y squared from both sides, and think of this as capital F of x, y, z equals 0. Remember, that's another way that we can describe a surface. So my tangent plane is going to look like the x partial, evaluated at the point 5, negative 3, 1, times x minus a, which is x minus 5, plus the y partial at 5, negative 3, 1, multiplied by y minus b, so that's y minus negative 3, y plus 3, plus the z partial, evaluated at 5, negative 3, 1, times z minus c, so that's z minus 1, equaling 0. That's going to give me my tangent plane to this surface. So I'm going to figure out those three partials. So f sub x is just 2, f sub y is negative 2y, and f sub z is negative 2z. So when I plug the point 5, negative 3, 1 into my x partial, I just get 2, so 2 times x minus 5. When I plug in 5, negative 3, 1 into my y partial, I get negative 2 times negative 3, which is positive 6, times y plus 3. And then when I plug that into my z partial, negative 2z, negative 2 times 1, so that's negative 2, times z minus 1 equals 0, and that's perfectly fine to leave the plane in that form. All right, here we have a function of x and y. We want to find all critical points and test them using the second derivative test to find local maximum and minimum points for this function. So first things first, we've got to find our x and y partials. So we get 3x squared minus 6y for the x partial, and for the y partial we get minus 6x plus 2y. We want to set them both equal to 0 and see what kind of critical points we find. So we want to try to pick the easier equation to solve and solve it for the variable that's easier to solve for. So looking at this, I would say that the second equation is easier to solve for y. So I'm going to add 6x to both sides, divide both sides by 2, I get y equals 3x. And now I can take that solution and plug it into the first equation. So I get 3x squared minus 6 times 3x equals 0. That's 3x squared minus 18x. I can factor that, 3x times x minus 6, and that gives me two solutions, x equals 0 and x equals 6. Since y equals 3x, my solutions are 0 and then comma 3 times 0, and then 6 comma 3 times 6, which is 18. So those are my two critical points. To compute my d value, remember d is f sub xx times f sub yy minus f sub xy squared. So what are my second order partial derivatives? Well, fx was 3x squared minus 6y, so this is 6x. fyy, that's just going to be 2. And then fxy is going to be minus 6. So plugging in the point 0, 0, so at 0, 0, d equals, well, that's going to be 6 times 0 for my fxx, times 2 minus negative 6 squared, that's negative 36. And since d is negative there, that means I have a saddle point. At the point 6, 18, my d turns out to be 6 times 6 times 2 minus negative 6 squared, which is going to work out to be positive 36. And since that's positive, and fxx, which is here, is also positive 36, so d is positive and fxx is positive, that means that I have a local minimum. So that means that 0, 0 is a saddle point, and 6, 18 is a local minimum. Last question is a Lagrange multipliers question. So we're given an objective function, 3x plus 4y, that's our objective, and then our constraint is x squared plus y squared equals 25. Remember that we normally rewrite that constraint so that it looks like g of xy equals x squared plus y squared minus 25 equals 0. So Lagrange multipliers, we set up equations that look like f sub x equals lambda g sub x, and f sub y equals lambda g sub y. So f sub x is just 3, and then g sub x is 2x. And then when we use our other equation, we get f sub y, which is 4, equals lambda times g sub y, which is 2y. So what we're going to do is solve both of these equations for x and y, and then plug into our constraint. That's a common method that we use. So we get 3 over 2 lambda for x, and 4 over 2 lambda for y. Now I know I could reduce that fraction, but it's actually going to make the algebra that I'm about to do a little bit easier if I don't reduce it. So plugging into my constraint, I get 3 over 2 lambda all squared plus 4 over 2 lambda squared equals 25. So that's 9 over 4 lambda squared plus 16 over 4 lambda squared equals 25. 25 over 4 lambda squared equals 25. 25 equals 100 lambda squared. Lambda squared equals a quarter, so lambda equals plus or minus a half. So that gives us two possibilities. Lambda equals a half, in which case x would equal 3 divided by 2 lambda, in other words 3, and y would equal 4 divided by 2 lambda, in other words 4. If lambda is minus a half, then x equals 3 divided by 2 lambda, which is minus 3, and y works out to be minus 4. So how do we know which of those is the maximum and which of those is the minimum? Well, we're going to take those two values and plug them into our objective function. At 3, 4, my function value is 3 times 3 plus 4 times 4, which is 25. And at the point negative 3, negative 4, my function value is 3 times negative 3 plus 4 times negative 4, which is negative 25. We get two values, so the bigger value is our max, and the smaller value is our min. And that's our solution.